So the title slide shows the topic asteroids, comets, and meteors. And the image here that you see on your screen in front of you is that of the very famous comet Hale-Bopp in front of the Mount Abu telescope observatory, 1.2 meter telescope. This was a film-based photograph, and the comet was very easily visible to the naked eye. That's why you see, even though the sun has still not set, we are able to see the comet and a few of the bright stars. Okay, so this was a very famous comet and a very bright one to start my career with, and it was quite a spectacular thing which motivated me to pursue this subject further. So with that point, let me just give you the what I'm going to talk about today. I'll talk about what are these objects and where in the solar system do we find them, how are they named, and what do we know about them, and how do we learn about these things. Okay. More details about how we learn about them, I think I'll cover in the next talk, where I shall be talking about telescopes for solar system studies. Okay, that will be sometime next week. So what are these objects and where do we expect to find them, right? So if you look at the these objects, mostly they are made up of rock and ice, and in fact comets are well known as dirty snowballs. Asteroids, having spent most of their time between Mars and Jupiter and closer to the Sun, are more of rock, and you have much less volatile material compared to comets. So the major orbit difference in the between asteroids and comets is the orbital parameters, where they are found, and what are the inclinations and perihelion aphelion distances to them. Okay, and what are the eccentricities, right? Meteoroids I will not talk about much, except to say that these are at the other end of the spectrum, very small bodies. Generally, there is a continuum between asteroids and meteoroids. And meteoroids are objects which are floating around in space, and these are sub-meter sized particles and boulders, which sometimes will enter the Earth's atmosphere and burn up. So those are what we call as meteors. Okay, meteoroids are much larger in number. We'll talk about the numbers shortly. Now, how do we identify the asteroids in the solar system? This is a map of all the known asteroids taken from data collected from the Minor Planet Center, and it's color coded for different types of objects. Let's not go into details here, but just to give you an example, this is the Sun, and the Earth is here, the Mars is here, and most of the asteroids are confined within the orbits of Mars and Jupiter being here. And Jupiter being so massive, it has a collection of objects at its L4, L5, and also the L3 points. And these are known as the Jupiter Trojans, the Jupiter Greeks, and the Hildas. Okay, so you have very prominent distribution which is co-moving with Jupiter. The main asteroid belt has several resonance features. We will, based on the orbit coupling with Jupiter, and you can also see that in this figure here, where, let me zoom in a little bit. I hope it works. So going outward from the Sun, very recently one asteroid has been discovered, which is called 2020 AV2, whose orbit is completely inside the orbit of Venus. Okay, so it's the first object to have been found of asteroidal nature which is within the orbit of Venus. Most of the near-Earth asteroids which we know about are either within the orbit of Earth or they cross the orbit of Earth. Okay, so there are several varieties which, based on their aphelion and perihelion distance, as well as their containment within the Earth's orbit, they are classified. So mostly we call them near-Earth asteroids when they approach close to the Earth. Then you have the Mars Trojans, and then the Hungaria group, which is just beyond the orbit of Mars. Most of the time they sit there. Then you have the 4-to-1 resonance from Jupiter, which causes the gap here. So objects which come in this gap get kicked out quite quickly. And then you have the inner main belt, the middle main belt, and the outer main belt. So 3 different belts. And then you have again several bands in between, which are populated by less number of objects because of their resonance with Jupiter. Prominent examples of these middle main belt are Pallas and Ceres. Ceres was in fact the first asteroid to be discovered between Mars and Jupiter, and people initially thought of it as a planet, but later on they found that there were many, many more objects to be found there, and Ceres was just the biggest of them all. The next one is Vesta, and then you have, of course, many other objects. And then you have much smaller numbers as you go further out, and then you have Jupiter with the Jupiter Trojans. Okay, so now let's come back to this, and let's look at what these tell us. What are the kind of numbers we know about them? So there are about 1 million asteroids known. Okay, and most are in the belt between Mars and Jupiter. Of these 1 million asteroids, about 27,000 have been named, okay, numbered. Numbered asteroids are those which have been, observed on, and their orbits are well known. They are generally classified into 3 main types. Depending upon where you read, you will find that they can be further subdivided into big number of classes from 14 to 24, depending upon very detailed spectroscopic classification. But loosely speaking, you can say carbonaceous types, metallic ones, and then the silicaceous or S-type asteroids. Size, as I said already, varies very greatly, and the largest one, Ceres, is nearly 1,000 kilometers across. Okay, I think I have an example of the pic, just to compare it. So this is, of course, the very familiar moon, Earth's moon that you see in the night sky. And this is Ceres, shown to scale, not at the same distance, obviously. And this is the other bright asteroid called Vesta. Okay, Ceres was the first one to be identified, and Vesta was the 4th one. So that is how the numbers 4 and 1 appeared before them. So these give you the typical sizes of asteroids, and in relation to the moon. Typical, I mean, for the largest ones. But typically, if you look at some of the other space asteroids which have been visited by spacecraft, you will see that there is a whole collection of sizes and shapes. Okay, and there are many, many more which have been recently visited. And fortunately, I don't have time to go into all of those in detail. But just to give you an idea of how very different kind of shapes we have. Mostly, they are irregularly shaped. Okay. Now let's come back to the orbital parameters of these objects, and we'll study the distribution of the minor bodies in the solar system. This is from Arvind's PhD thesis, and what he did was to use the data from the Minor Planet Center, which is a body of the International Astronomical Union, and they compile and maintain the details of all of the orbits of all the minor bodies. Okay, and so here you see in log scale on the x-axis, you have the semi-major axis, and that is the distance from the sun, and on the y-axis you have the eccentricity. Okay, so objects which are in large fonts, large symbols here are basically the planets which have eccentricity very close to 0. Mars is here, and then you have Jupiter, then Saturn, Uranus, and Neptune. Okay, so this is in log scale, just remember that. So it's quite misleading to see Saturn and Uranus and Neptune being so close to Jupiter. Okay, but then when you consider them in log, you understand the size. So typically these asteroids are all lumped together in one color because he was more interested in comets. So we started looking at those. And then among the asteroids, you also have a few objects which show comet-like properties. Okay, so these are called the main belt comets. Okay, And these are objects which have been discovered only in the last couple of decades. And these are, most of the time, they have asteroid-like behavior, but sometimes they show comet-like coma and tail. We'll come to what comets are in a short while. Subsequently, what we have seen is that there are all these other objects called trans-Neptunian objects, centaurs, scattered disk objects. And before that, of course, you have the Jupiter family comets, which have numbers, which have their periods around 20 years, up to 20 years. And beyond that, you have the long period comets, okay, which are distributed all across. And typically, long period comets have very high eccentricities, nearly parabolic orbits for many of them. Yes, that's the way the distribution looks like. You can draw similar diagrams with the inclination and other parameters, but I will leave that as an exercise for you all to try and come back with interpretations. Okay. Next, let us see how the comets look like if you look for them on the face-on view of the solar system. So again, here this is the Sun at the center, and then the innermost planet which is shown is Jupiter. You have the scattered disk objects here, and then basically the Kuiper belt, which is the place from where comets like Comet Halley come. Okay, you have the outer. So these are all basically from those. The color codes mean something, but let's not go into the details. You can also look at how the comets are coming from their distribution in the in inclination. Okay, so from the inclination, if you see, then you find that most of the long period or single apparition comets come from spherically symmetric directions. So it's, as far as the solar system is concerned, they can come from any direction. Okay, so based on that and on the very large semi-major axis, it was proposed by Oort in the 1950s that this is coming from a spherical cloud of comets, and this cloud is distributed all around the sun, okay, because of various reasons. Later on, models have shown us that it is because of the early formation or history of the solar system that this Oort cloud was formed. It was basically by the actions of Jupiter and Saturn when they moved around in the during the time of formation that they kicked out material from the inner solar system. And the kicked out material went to all directions, and most of them ended up in the Oort cloud. So in fact, the Oort cloud is a kind of repository of material from the time of formation of the solar system. So objects from the Oort cloud still bear some signatures of the time of formation. So if you can study the samples of these objects, then you will be really studying the very primitive or early solar system. Let's look at how that appears if you were to see it in a three-dimensional distribution. So I had spoken to you about the Kuiper belt and the outer solar system. So this, for example, is Pluto's orbit, and you have the inner solar system, I mean, inner in the sense that inner to Pluto here. And you have the Kuiper belt objects, which are all confined within this small disk here. Okay, and the Oort cloud is this cloud of comets all around, and it can have I mean, these are estimates that there may be billions or even trillions of comets in the Oort cloud. So these are estimates, and then in fact nobody has ever really seen this Oort cloud kind of feature in any other stars, although you expect that given the similarity in the formation scenario, you should be able to see this. But it just means that the numbers are although the numbers are large, but then the size of the objects are very tiny, so they are very diffuse. Okay, so not much is. So let's come back to what are comets. So as I said, they are mostly rock and ice, so-called dirty snowballs, and they are orbiting the sun with most of the time away from the inner solar system, most of the time spending their as cold bodies and without any kind of features. Typically, they are a few hundred meters to a few kilometers in size. Hale-Bopp, for example, was about 40 kilometers, one of the biggest known in recent times. What we do know is that they form a very prominent tail when they come close enough to the sun. So this happens because the ice which is embedded in the nuclear surface gets sublimated and releases along with the dust, and both of them get pushed out, the dust and the gas, and they follow along the orbital path. So these comets might be, as I already said, they may come to the sun once, or it may be a periodic visitor to the inner solar system, depending upon where they are coming from. Why should we study? I think I already mentioned this in some extent. They spend most of the time far away from the sun, which means that their material is not really much weathered. And so they can be considered to be really leftover material from the time of formation. And therefore, they are the ideal objects to understand the formation and evolution of the solar system. And on the other hand, every comet has a different and unpredictable behavior. So it is important to study each one for its own sake as well. So we can classify comets on the terms of their period as well as the reservoir from which they are coming. So comets with orbits orbital periods less than 200 years are called short period comets, and those with longer than 200 are long period, obviously. You also have Jupiter family comets, which are like Comet 67P and 2P&K. These are objects which are relatively short periods, up to about 20 years. And comets from the Kuiper belt are those coming from the trans-Neptunian region and have slightly longer periods, around 40 to 60 years. A typical example is Comet Halley at 76 years. And then, of course, you have the Wood Cloud comets, which are mostly one-time visitors, or they may, after their first visit, they may become a periodic comet eventually. And then recently, as I mentioned, there have been the discovery of the main belt comets among the asteroids. And these are also quite interesting objects to learn why they are showing activity, although they are having orbital parameters like the asteroids. In fact, some people call them active asteroids. So I should be moving quickly now. The comet naming is like this. We use P for a periodic comet, C for a comet that is not periodic or for which we don't have the full information. X is a comet for which a meaningful orbit cannot be computed. For example, if there were very few observations which were made and we lost the object for whatever reason, okay, we could not observe it again. D is for a periodic comet that no longer exists. For example, there are comets which either get eaten up by the sun or they collide into Jupiter. There are some very famous examples from the 1990s, Comet Shoemaker-Levy 9, which went into Jupiter. And then you have very recently the only two interstellar objects which have the prefix I. And this is used for comets as well as for asteroids. So after this letter, you add the year of discovery and then uppercase letter identifying the half month of the observation, as well as a number in the order of discovery within that half month. And to complete the designation, the name of the discoverer are added on at the end. Okay, so this is how comets are named. Now, if we come to asteroids, these are a more interesting set in terms of naming, because they are in such large numbers. And asteroids typically we are discovering on almost a daily basis by repeated imaging of different regions of the sky. And what these objects are given names are the year of the discovery, followed by a letter representing the half month of the discovery, just like in comets. But at the end, because the numbers are large, we also have a letter and a number indicating the discovery sequential number. Okay, for example, 2004 MN4. Okay, this is also known as the asteroid Apophis. I will tell you about Apophis shortly. The names can also be suggested by the discoverers as well as a committee of IU members, and but they need to be ratified by the Small Bodies Working Group and published in the Small Bodies newsletter bulletin. Okay, and Small Bodies Network bulletin. So one example of such a publication is that of Kumar Venkatramani, who also did his PhD from PRL. He is one of the few Indian astronomers to have an asteroid named after him. And this asteroid was earlier known as 2000 SM whatever. And it's numbered like this, 32483. That's the asteroid number since it's known. Now, about 27,000 or around 28,000 asteroids have names given to them based on the proposals which have been accepted so far. So that's how the numbers are, the asteroids are named. So as I was telling, asteroid Apophis is an interesting object. It's a potentially hazardous asteroid, which was discovered in 2004 with the designation 2004 WMN4. And soon after discovery, within a few weeks, it was found that there is a 2.7% chance of collision with Earth in 2029. So this was quite a terrifying thing for all astronomers, and it was there's a flurry of observations which were made for understanding the orbit of the asteroid. And these follow-up observations resolved the situation, and it was found that it will not be, there's no chance of a collision with Earth, at least for the next 100 years. During 2029, it is expected to pass between the Moon and the Earth. So it will be sailing just above the geostationary satellite locations. So we are safe in that sense. So these PHA are near-Earth asteroids which can come very close to the Earth and which are brighter than a certain limit, okay, which has an implication on the size of the asteroid, because smaller objects keep hitting the Earth very regularly, and we do not really need to worry about those. But objects which are of Apophis size can cause large-scale devastation. Apophis, for example, is about 370 meters across. Okay. Now, getting back to comets. We'll just visually look at some of the very interesting comets which have been visited by spacecraft, as well as which have interesting images and science related to them. Comet 67P was discovered by this Russian duo of Churyumov and Gerasimenko, and this was visited by a ESA spacecraft called Rosetta. It also had a lander called Philae on it. And although Philae was not completely successful, Rosetta itself was a grand success. And they really had a huge suite of instruments on board. And I do not have the time to cover all of that, but I'll just show you some example images from Rosetta. This is one picture from the NavCam on the Rosetta mission. And it shows very nicely the dual lobe feature of this comet, and also more interestingly the jet which you see in comets. Okay, so this is the dust jet coming out from the from one of the pits on the comet. Another example pic is this one, which is showing you the landscape over the comet on a much smaller scale. It's I should have mentioned that this image is about 4.3 by 4.3 kilometers across, and the comet itself was about 6 kilometers in size. This one is much smaller field of view, and in fact, it looks not very different from a polar or Himalayan landscape. Sometimes you might have seen such pictures, but this is from the Rosetta spacecraft. Now let's look at some other interesting comets, just to understand what comets look like and what we can tell about them from the view of the images. This, for example, is one of the most famous comets of the last few years, Comet Neowise, and this was discovered in 2020. F meaning somewhere in the middle of the year, just before the and In fact, it was monsoon time for us in the rest of the country, but fortunately, it was quite clear and successfully observed in Ladakh at the Hanle site of the Himalayan Chandra telescope. And Dorje Angchuk of that observatory was able to take this kind of a fantastic mosaic of images of this comet. He positioned his camera about 1 kilometer away from the dome, which you see in the foreground here, and the comet is in the backdrop. Now, what is of interest here is the tails which you can see. Okay, so comets, as I had mentioned, they have a very spectacular tail when they come close to the sun, and they end up having two tails. In fact, sometimes you see another tail also. We'll talk about that if time permits. So this is the ion tail. Okay, so this purple blue color tail is the ion tail, and you have the dust tail, which is curved like this. Okay, so the ion tail basically goes along the is just pushed away by the solar wind directly. Okay, so that's how it is, just radially outward, pointing away from the sun. Whereas the dust tail is ejected by the comet, and since it has some mass, it also continues to have some momentum in its orbit, and it also gets pushed away by the solar wind. So that is why you see a curved behavior here. Further changes in geometry can also, like the viewing angle of the orbital plane, will matter in terms of showing us different facets of this. We'll just see some movies to show you how this looks like. This, for example, is Comet Hyakutake, 1996 B2. This was, in fact, quite a spectacular comet, and it was a very fast-moving comet. And you can see here very well how it is rounding the sun. The sun is behind this occulting disk, and this cloud structure which you see here, I'll just stop it here somewhere. So here you see the dust tail, and then you see the ion tail very, very nicely as a very thin and sharp feature. Okay. And it's always pointing away from the sun, as you can see in this video. Another example is Comet Lovejoy. This one is in fact quite spectacular in the sense that it comes so close to the sun that it completely, the tail detaches from the comet. Okay, and then after it comes back out from behind the comet, the tail reappears after a while. You can see it in this video. Stop it here just a moment. So don't worry about this. This spike is something which is to do with the electronics. The comet is extremely bright, and so that's why the image appears saturated and this kind of linear spike. That's an artificial thing. But what is interesting is this dust tail and the ion tail. Now watch what happens when it comes very close to the sun. Okay, it's just gone beyond, and then now the tail is completely missing. Here it starts regrowing. Okay. So this comet, in fact, has a very interesting history if I were to go into it. But after perihelion, it provided very spectacular images. This is from the ISS. This one is from an observatory site in Chile. And then another example is Comet Pan-STARRS. As I said, so here you see the ion tail very briefly, but then mostly the dust tail in this fan shape. And this is another view of the same comet with the fan shape. And if you want to have a more understanding of this shape, I would urge you to go and look through this link. Okay. The same comet, when we looked at it, when the Earth passed through the orbital plane of the comet, it showed a very, very long tail. Okay, almost 90 degrees across the plane of the sky. So you can trace the image of the tail. So this is basically the orbital plane of the comet, and the material left in the plane by the comet when it passed through, it's still radiating or scattering light away from the sun towards us. So that's how this I will, I think, skip quickly because I want to cover this again in the next time. It's just to show you that spectroscopically comets look very different. Most of the time they show us this kind of diatomic and triatomic carbon, and then CN molecular emissions. But there are also times when we see quite different behavior, which are just examples taken from the work that we have been doing at Mount Abu Observatory. I will just quickly talk about one particular comet, which was the interstellar comet. It was a real visitor from the stars. Arvind and colleagues managed to study this object with a 2-meter telescope, whereas worldwide it was studied by larger telescopes. This object had it was the first interstellar comet ever to come to the inner solar system. And how do we know it was interstellar is because it had a hyperbolic orbit with a very high entry velocity, okay, which implies that the comet had an interstellar origin. What we found that it had similar behavior like the carbon depleted comets of the solar system. In fact, there were very interesting studies, results coming out from this. You can go into it in more detail if you want. You can go through the paper. Okay. Now I'll just show you one more image. This is another comet C2013 R1 Lovejoy. And since it may not be very easily visible, I'll just point to you that this is the comet. And in fact, this one, which you might have been inclined to think as a comet, is actually a meteor. Okay. And this is the boundary layer as seen from the Mount Abu Observatory. So whatever, so the atmosphere is completely clear above it, and you have all the pollution settled below this 1 kilometer altitude. So these meteoroids are meter size or smaller objects which orbit the sun. Every once in a while, their orbit intersects with the Earth, resulting in what we see as meteors as they burn up in the atmosphere, right? Now, many of these meteoroids are left over by comets. As I showed you some of the photos, they leave a lot of dust and material as they orbit the sun. Now, when these orbits intersect with the Earth's orbit, they can enter the Earth's atmosphere in very large numbers, and thus causing meteor showers. Okay, so one very famous shower which should be brightening up this week, in fact it's all a very interesting time to go and see it, is the Eta Aquarid. It's mostly visible very well in the southern hemisphere, but even in the northern we should be able to get a good view. And there are some reports that this might be the best in this century for this particular shower. It is associated with the dust left behind by Comet Halley. Okay, so twice a year we have this orbit intersection. And this is an example of some of the meteors which entered the Earth's atmosphere in about 2 years ago. And this is taken at the high altitude desert of Alma Observatory, so it's about 5,000 meter altitude. And if you would, I'll just zoom in and see if I can. No, I can't. So these tracks are shown here. So these are the tracks which are all coming from the same, which all appear to come from the same point here. Okay, so this is the location of the star Eta Aquarius, and that's how the name comes, Eta Aquarid. Okay, and so this kind of showers are seen annually in many months around the year. The Leonids are another very famous example, and the Geminids. We'll go into more detail later on if there are questions. So typically, these meteoroids are meter size or smaller objects, and normally we don't really see them as asteroids. But once in a while, when they come close to the Earth, we are able to actually track them. And there have been a few objects which have been identified first as near-Earth asteroids, and later on, they were tracked, and they were predicted that they would be falling at this land, such and such location. And people have actually gone and been able to identify them as they entered as a fireball. And subsequently, in fact, in some cases, even meteorites have been collected from the site where it has fallen. So these meteorites, of course, are the subject of the next talk. So I will quickly stop here with just one final pick of another comet, simply to show you how spectacular these objects are and how varied their appearance is. This is a famous green comet of 2022. And this was again taken by Dorjangchuk in Hanle, and it covers a very large field of 10 degree by 9 degree. Okay, so the moon, for example, is just half a degree across in the sky. What we did was to observe the very innermost part of this comet using our 2.5 meter telescope last year, and it shows you very well the inner coma, which appears white because of the dust, and then the green because of the diatomic carbon and the other molecular emissions which make up the very green colors. So I think I'll stop here and take questions.